My name is Roland Koo. I'm the product line manager and a CAS research staff member for compilers. Today I'm going to share with you information on a project which we collaborated with McMaster University. The title is MAS for Cell Broadband Engine. Let me introduce you to the team. There are many people involved in making this project a success. This project was led by Professors Christopher Anand and Wolfram Call of McMaster University, and Robert Anninkel, who is the tech lead for IBM MAS library development. Let's talk a little bit about the research. MAS stands for Mathematical Acceleration Subsystem. It consists of libraries of mathematical intrinsic functions that are highly tuned to IBM processor architectures. Before this project, MAS is already working with XLC and C++ and XL Fortran compilers on Power and BlueGene architectures. The goal of this project is to enable MAS to run on Cell Broadband Engine processors. Cell Broadband Engine is a hybrid architecture, and therefore it is extremely difficult to program. Traditional programming models do not work, so we need a new approach for this solution. IBM was also trying to introduce QS21 and QS22 blades to the HPC space, and this requires a highly tuned math libraries to help make multi-core and SIMD programming easier for users and improve the exploitation and performance of the SPE. We need to explore new ways of enabling MAS libraries on new platforms using the Coconut technology. Here's a brief introduction of Coconut. Coconut stands for Code Construction User Tool. It is a research program in McMaster led by Professors Christopher Anand and Wolfram Call. Coconut is an experimental code generation tool that allows rapid prototyping of design patterns and compiler optimizations for new hardware. It also has mechanisms to improve program reliability. The team built a prototype to improve single precision performance of MAS libraries for Cell SPE. Test shows very good result. We actually saw improvement in both accuracy and performance. We also found that the new mathematical functions can be created in a relatively straightforward way using Coconut. The team then went on to investigate if we can produce an equally as good a double precision version of the MAS library. Again, the prototype showed very promising results. As part of the exercise, we also discovered that the Coconut technology has additional benefits. It can help compilers improve the exploitation of new multi-core processor architectures and also shorten the time to implement new math functions like MAS on new platforms. Let's move on to the harvesting stage. The QS22 blades needs a set of highly tuned single precision and double precision mathematical libraries to optimize the performance for the SPE components of the Cell Broadband architecture. MAS supports both scalar and vector functions and is already shipped with XLC and C++ and XL Fortran compilers, and it's already running on AIX and Linux on Power and BlueGene platforms. So MAS becomes a naturally good fit for the Cell platform because it can exploit the multi-core architecture. The team has successfully created a working prototype of single precision and double precision versions of the MAS library for the Cell Broadband Engine. So we compared a single precision MAS library prototype with the SIMD math library, which is already shipped with the IBM Software Development Toolkit for Cell Broadband Engine. We noticed a significant performance improvements on the SPEs. We went on and produced a full prototype of the double precision MAS library for the SPE, and we were quite successful, and the test results looks very good. So at this time, we're quite confident that we can in fact productize both versions of mass libraries for the Cell Broadband Engine platform. Besides the Cell Broadband Engine, this project also have additional harvesting opportunities. We can leverage the Coconut technology and lessons learned in this project to help IBM compilers improve exploitation for future multi-core processor architectures, and also improve the functionality of mass libraries and perhaps other mathematical libraries. So what do our stakeholders think of this technology? The final single precision mass for Cell SPE achieved about 4 times the average increase in throughput over the SIMD math library, which is shipped in the SDK. And the double precision version of mass library achieved about 5 times average increase in throughput over the SIMD math library. So both versions of the mass libraries were released in 2008. With XLC and C++ for multi-core acceleration for Linux version 10.1, and it's also shipped in the SDK, the IBM Software Development Kit for multi-core acceleration version 3.1. Look at the customer benefits. Now customers can simplify multi-core and SIMD programming effort on the Cell Broadband Engine platforms, namely the QS21 and QS22. It also allows customers to get the most performance out of the Cell Broadband Engine platform by leveraging the mass libraries that are optimized for this processor architecture. And this will also help shorten development cycle and reduce project risk and cost. Business impacts and results. Mass library for Cell Broadband Engine greatly improved the overall value proposition for the QS21 and QS22 blade. And it also helps simplify the multi-core and SIMD programming effort while improving performance and exploitation of the SPEs. By enabling the mass library on Cell platforms, it also improved portability between the Power, BlueGene, and Cell platforms. And double precision mass library enabled the QS22 machines to compete in the HPC and financial services sectors. So it's opening up new market for these hardware platforms. So overall, I'm very pleased that this technology has found a home in a product. We also have a lot of opportunities to make use of this technology to help deliver performance for future IBM multi-core processors. Thank you for listening.